In a previous video, we said that the derivative of the exponential function b to the x is given by b to the x times the natural log of b. One way of verifying this is by using chain rule. In particular, it's possible to rewrite the expression b to the x as follows. Because the natural exponential function and the natural log function are inverses of one another, we can write b is equal to e to the natural log of b. With this way of thinking about b then, the expression b to the x becomes e to the ln b all raised to the power x, which, by a rule of exponents, is just e to the ln b times x. This is an expression we can now differentiate using chain rule. Indeed, the outer function is just the natural exponential, so chain rule says that the derivative is given by e to the ln b times x times the derivative of ln b times x. The derivative of ln b times x is just ln b, so this means that the derivative is given by e to the ln b times x times ln b. But remember that the first term is just b to the x, and so in total then, we obtain a derivative of b to the x times ln b, as we've seen before. Equipped with this derivative then, implicit differentiation allows us to compute the derivatives of log functions. In particular, the log base b function satisfies the identity that b to the log base b applied to x equals x for each x in the domain of log base b. We can then take the derivative of both sides with respect to x. For the left side, we use chain rule. The outer function is the exponential function with base b, and so chain rule says that the derivative is given by b to the log base b applied to x times the natural log of b times the derivative of log base b applied to x. For the right-hand side, the derivative is just 1 because the derivative of x is just 1. Now we can simplify the left-hand side a little bit because b to the log base b applied to x is just equal to x, and so the left-hand side just becomes x times ln b times the derivative of log base b applied to x. Isolating the derivative of the log base b term, we find that it's equal to 1 over ln b times x. So this is the derivative of the function log base b applied to x. One particularly important log base is the number e, for which the function is just called the natural logarithm, and its derivative in that case is given by 1 over ln e times x, which is just 1 over x. In other words, the derivative of the natural log function is just 1 over x. Equipped with all of these derivatives then, it's possible to compute the derivatives of even more complicated functions, such as those for which x appears in both the base and the exponent. For example, let's look at the function f of x equals x to the x, and let's try to compute its derivative. Well, at first glance, it appears that f is a power function, and so naively, power rule might be tempting to apply, which might suggest that the derivative is just given by x times x to the power x minus 1. But this turns out to be entirely wrong. Instead, it's useful to think of f as the function that is e to the x times ln x, and then differentiate this expression. Indeed, once we think of f in this way, we can differentiate using the chain rule to obtain a derivative of e to the x times ln x times the derivative of x times ln x. The derivative of x times ln x can be found using the product rule, and we can write its derivative as d dx applied to x times ln x plus x times d dx applied to ln x. The derivative of x is just 1, and the derivative of ln x we just computed to be 1 over x. Making these substitutions then, the full derivative becomes e to the x times ln x times the quantity ln x plus 1. Now, the first term is just x to the x, and so the derivative becomes x to the x times the quantity ln x plus 1.